everyone, welcome. We're coming live to you from Amsterdam. My name is Remco Overdijk. I've been at bolcom as a systems engineer for over 3 years now, and I'm currently working in our compute infrastructure team. Our team deals with all types of infrastructure, especially compute, ranging from bare metal and virtual machines in our data centers up to Kubernetes in the Google Cloud and everything in between. We also play a pivotal role in the transformation of our infrastructure to the public cloud, which not quite coincidentally is also the stepping stone for today's story.
Hi, I'm James Brook, and I'm a solutions architect at Google Cloud. My team works with some of Google's largest customers, and we help them to solve difficult and interesting engineering problems. I'm also a service mesh enthusiast, and I've been following the technology from the very beginning. I'm not actually part of a team working directly on service mesh, but I have been involved with the service mesh project at bol.com from the first planning meetings right up until today.
Bol.com as a company needs little introduction for people living in the Netherlands, since we're a familiar name in Dutch e-commerce. With a large number of partners selling their wares through our platform, combined with a rather large selection of products of our own, we're the first stop in online shopping for a large portion of Dutch and Belgian customers, enjoying same and next day delivery and excellent customer support. Being a major e-commerce platform takes a lot of hard work and infrastructure. We've experienced a steady growth in the past, allowing us to employ an ever-increasing number of people, many of them focusing their attention on solving IT-related problems to stay ahead in this competitive market. With the amount of teams we employ, staying agile is key. As such, we feel it's important for our featured teams to be able to work independently without having to wait on platform teams to deliver or maintain their infrastructure for them, for example. That's why we believe that self-service infrastructure is the future for us. At bolcom, we're used to doing things ourselves. Much of our infrastructure still lives in our private data centers. And being in online retail, there's obviously very significant seasonal variation in both our business and traffic. Historically, we've been statically scaled for the busiest day of the year, plus a little safety margin. We do have lots of automation and manage our machines using Puppet. Software development teams can deploy their applications in our data centers using automation, but all of the infrastructure interaction on their behalf is left to site reliability teams. We really believe in DevOps, and we want to allow teams to really focus on building applications and not all the other stuff. In a data center, self-service is partially possible, but it's a bit obscure and inflexible. Our philosophy is you build it, you run it, you love it. To further embrace that mantra, we try to increase the level of self-service we offer. Granting autonomy and sharing ownership and a true DevOps way of working turned out to be hard in our current setup. Separation of concern was a real issue. We just couldn't find a way to hand over the pagers to application teams. So how could we get more autonomous teams? We started by integrating public cloud into our platform catalog. The idea here was to combine elastically scaling infrastructure with a truly programmable interface with APIs that could cleanly separate concerns for developers as well. Newer applications nowadays are deployed to Google Kubernetes engine, a managed Kubernetes cluster on top of the Google Cloud. The applications that we deploy are built or rebuilt specifically to take advantage of the cloud and Kubernetes. Our ecosystem of automated platform tools now has first-class support for the way we use cloud services as well. Developers get to write a Kubernetes-like manifest to deploy a rich set of GCP resources, which in turn are deployed by a centralized tool. Application teams can build their own CI/CD pipelines in GitLab and mix and match supported GCP products based on their requirements. Moving to the cloud, together with regulations like GDPR, also affected the way we needed to think about security. The platform gives freedom, but it also enforces policy guardrails at the same time. Given the scalability of Kubernetes, the original idea we had was to have a single cluster per environment in order to reduce the overhead. These multi-tenant clusters house all of the different applications and services, isolated into namespaces, and are able to connect to each other using network policies. This worked well for a while, but some mistakes were made along the way. One in particular. Since we want our GCP services to be reachable from our data centers and vice versa, They're using private interconnects to form a large private network, sharing the same Class A network. This also means that we had to use our IP subnet space sparingly. Given that we had around 400 microservices in the data center at that time, initially we figured that having 1,024 services in a single Kubernetes cluster would be plenty. And as such, we set up the GKE clusters with a /22 subnet for services, allowing for 1,024 services. At that time though, we overlooked the fact that almost everything, including monitoring, requires a service in Kubernetes. We also underestimated the popularity of the self-service model. And soon we saw a rampant growth of new services being used for all kinds of proof of concepts and new microservices. This ended up being a bit of a crisis in the end. We came very close to hitting the service limit, effectively halting the creation of new services in that environment. Unfortunately though, once the clusters were created, it was not possible to increase the size of an assigned subnet without recreating the entire cluster. Moving all of our hundreds of workloads to a bigger cluster would have been a major project and still wouldn't be completely future-proof, since extremely large Kubernetes clusters are certainly possible, but come with a new set of scaling challenges. So we concluded that we needed multiple clusters per environment and treat them as cattle rather than pets. And I guess that's our first lesson to share today. Put plenty of thought into your IP subnet allocation strategy. Believe it or not, this was actually the primary reason for looking at a service mesh in the first place. So, we knew we needed multiple clusters. We had quite separate cloud and data center worlds. We had many different ways to load balance and discover services, and there wasn't even really an easy way to find a service either. Now, service mesh definitely seems to be somewhere on the hype circle, or at least it was a year ago. But we really did not set out to justify having a service mesh because we thought it was cool. In fact, quite the opposite. We were a little scared of the idea. We did everything in our power to go multi-cluster without service mesh. Service mesh is definitely complex. It's not a mature technology either. We had experience with that from gambling on Kubernetes when it was still young. But we started to think seriously about a service mesh, and some bonus features started to become quite apparent, like strong identity. Mutual TLS authentication and authorization for services would make it much easier to please our security teams. We read about mesh expansion. The idea of seamlessly expanding the mesh to machines in our data centers really appeals to us as well. We worry a lot about data exfiltration, and the concept of filtering outbound traffic based on request URLs using egress gateways seemed promising. We approached planning and feasibility research very carefully and appointed the project manager and formed cross-functional working groups to figure out particular details. Key criteria for selecting a product included multi-cluster support, mesh expansion, since eventually we want to incorporate our data centers into the same mesh. It should support egress gateways because egress gateways would provide the support needed for filtering outbound traffic, and a strong community. We evaluated all the available options at the time, but this being about 18 months ago, Istio was really the only product that provided both multi-cluster support and ticked all the boxes or would have upcoming support for those wishes on a relatively short term. Our close cooperation with Google also meant that we had access to Istio developers, which proved to be very useful, and we'll touch on that later as well. Service mesh technology has come a long way in these past 18 months, and the available options are now more mature, more diverse, and tailored to specific scenarios as well. Linkerd, for example, recently launched multi-cluster support, so make sure that you do a proper product selection based on your requirements before diving in head first.
Okay, we said this wasn't going to be a what is service mesh talk, but we are going to deep dive into some of the things that were particularly relevant to the journey. As you probably know, Istio's data plane is made up of Envoy proxies. So typically on Kubernetes, an Envoy proxy gets injected into each of your application pods. You see the Envoy referred to as the service proxy or the Sidecar. The Istio control plane watches the Kubernetes API server and maintains a registry of all the services in the mesh. And it uses that registry, along with the Istio configuration that you provide, to manage Envoy proxies using the Envoy XDS APIs. And that's how a load of separate envoys are formed into a single mesh. Once services have an Envoy sidecar, the proxies become directly responsible for all of the routing of your service-to-service traffic. For the client-side load balancers, Envoy maintains clusters of healthy endpoints. That's not Kubernetes clusters. So it's definitely useful to have a pretty good understanding of Envoy terminology if you're serious about doing mesh. Each endpoint in a cluster is simply the destination IP address for a pod and a port. The traffic flows between pod IP addresses and doesn't follow the usual IP tables routing which is programmed by kubeproxy and Kubernetes. By having a service mesh running across multiple Kubernetes clusters, we hope to make the cluster boundary much less significant. Client-side load balancing is one of the most powerful concepts in service mesh. And the bol.com GKE clusters are set up to use VPC native networking, which basically means that pods get an IP address from a reserved subnet in the VPC, and all of the pod IP addresses in all of the clusters are directly routable in a flat network. With client-side load balancing, Envoy proxies can seamlessly send traffic to endpoints on any GKE cluster that is in the mesh, as well as other network locations that are part of the mesh. And a nice side effect of that is a lot of separately managed internal load balancers can now be deleted. So, zero trust networking. We originally expected to hear an audible groan when you heard this jargon mentioned, but this talk's recorded, so it doesn't matter now. It sounds like jargon and marketing hype, but it's important. Security is really important to bol.com, especially in these days of GDPR regulation. Here's how Istio and Envoy help. Each service gets its own identity, and the important thing about that identity is that it truly represents the application, unlike an IP address, which in the Kubernetes world is something very ephemeral. We want applications to be able to communicate with each other, but we need a way for applications to trust each other based on their identity and not an IP. And for that to happen, we need a few other things. Credentials. So these come in the form of TLS certificates. Mutual TLS provides the means of authentication. And for those of you who haven't run into mutual TLS, it's very simple. It just uses an optional feature of the standard TLS handshake, so that the client also presents the certificate and the server verifies it. And of course, mutual TLS gives you encryption too. And then finally, authorization. Now that we have identity and authentication, we have a policy API to say which services are allowed to talk to each other. Later on, we found that there were some caveats to zero trust with service mesh alone, and we'll get to that soon. So it's clear that this was not a so-called greenfield deployment. That would have been a wonderful luxury. Bol.com are running hundreds of applications using all sorts of different technologies. Being able to migrate incrementally was a serious concern, and it turns out rightly so. This was the hardest and most time-consuming part of the project. And this is what we are getting at when we talk about weaving the mesh. An application becomes part of the mesh when an Envoy service proxy is injected as a sidecar, and the pod's network is programmed so that all traffic entering and leaving the application is handled by Envoy. In this project, we were only focused on enabling the sidecar. Don't start using any of the features yet. Only when you've got the sidecars in, then start using features and realizing the benefits. At a really high level, we planned several phases to weave the mesh. Lots of preparation, enabling sidecars in permissive mutual TLS mode with something called auto MTLS turned on, enabling authorization policy, switching mutual TLS to strict mode, disallowing plain text connections, and then eventually cleaning up all the loose ends and start adding more features. And broadly, each step depended on the previous step for the whole mesh. We knew the adoption would have to happen incrementally, namespace by namespace, or even by workload, and we would depend on lots of different application teams. Initially, developers were given the option to opt in to having the sidecar in their workloads. Emails were sent, documentation was shared, people were nagged. At some point, the majority of applications had been migrated, and after that, sidecars were injected by default. Developers still had the option to opt out if they really needed to. So what's the big deal about enabling the sidecar? Surely you just need to label a namespace or a deployment. It turned out that enabling the sidecar was messier than expected. More effort went into rolling out service proxies to the existing applications than any other part of the project. Remember, there are approximately 500 services using all kinds of different technologies and protocols. So we're going to talk a bit in more detail about some of the things you need to think about when adding sidecars to your applications. There are some simple things that you just have to get done. For example, if you want HTTP-related functionality, Istio needs to be able to figure out that you're using the HTTP protocol. You need to prefix the port names in your Kubernetes service with the protocol. Envoy seems to do some HTTP response validation. A malformed response header could trigger a 503 error. So that just comes down to testing and fixing. Our applications are monitored with Prometheus, and the logs go to Elasticsearch. When you enable restrictive policies, you have to make sure your observability tools just keep working. And probably the most obvious thing is that sidecars don't come for free. There are thousands of pods in the clusters, so that we knew that there would be thousands of extra containers. And that's overhead you need to plan for. You can see it as a tax you get to pay for the benefits of service mesh. And there are ways you can minimize it, just like tax, and there are various related things to watch out for. You need to think about what happens when your pods start and stop. Things were not as we expected here, and we'll talk about that. And what if your application just doesn't work well with service mesh? You probably don't want to compromise on your zero trust ideals. So we ended up accepting that exceptions are a reality, and we found an interesting way to solve that. But before we dive into some of that, there was another major issue we ran into that luckily you don't need to worry about now. And we picked up a couple of best practices. Remco is going to tell you all about that.
We deployed our GKE test environment on Google preemptable VMs, which can disappear with a few seconds notice. This turned out to have an unexpected benefit. They served as an excellent chaos monkey. When a service proxy comes up as a sidecar inside a pod, by default Istio uses an init container to reprogram the pod's network, so that all TCP traffic in and out of the pod is handled by the proxy. We decided not to use the default network capture mechanism because we had concerns about privileges, because the init container needs netadmin capability to modify IP tables. That basically meant that we would have need to grant that privilege to anyone and anything that could make a deployment onto our Kubernetes clusters. Luckily, there was an alternative, an Istio CNI plugin, which does not need those elevated privileges. Unfortunately, our preemptable chaos monkey exposed the problem. Pods on a VM that just got preempted would often come up without the IP table rules being properly updated. Not necessarily an issue if you don't use preemptable VMs in production, but the issue might occur there as well under other circumstances. Another piece of luck here is that we happened to be at KubeCon San Diego at the time when we noticed the problem. James was there as well, and he tracked down some Istio contributors, and we managed to find the cause by sitting at the booth. It turned out to be a race condition with Calico when new nodes came up. That issue is solved upstream now, so it won't bother anyone anymore. So there's two suggestions here. You could use the Istio CNI plugin for network capture rather than the default behavior, and do some chaos testing. Preemptable VMs helped us in the beginning, but we ended up deploying a tool to randomly kill pods in the end as well.
Let's talk about the overhead of the data plane. When the sidecar container is injected, some resource requests and limits are set. As you can see from these tables, ultimately we were able to substantially reduce the default limits that Istio sets. One thing to watch out for: resource quotas are used on the namespaces at bolcom, and adding a bunch of sidecars could easily push a team above its limits. So be prepared to adjust these, or you might not even be able to start pods. The proxies don't buffer traffic, and the potential throughput in requests per second is generally determined by the available CPU. Our limit of 0.4 CPU per proxy gets us about 700 requests per second. One thing that made a dramatic difference to memory consumption was limiting the configuration scope of the proxies by segmenting the mesh. More about that in a moment. If you use the horizontal pod autoscaler, you need to think about that too. It works by summing CPU requests for all the containers in pods. Adding the sidecar can easily skew the thresholds at which autoscaling kicks in. So you may need to tune your autoscalers to avoid not scaling soon enough or wasting resources. Obviously, not every application is the same. Because of that, we needed an easy way to tune proxy resources per deployment. For example, we might have applications that do lots of heavy processing, but don't handle many requests, or vice versa. Istio supports resource annotations, which teams can simply add to their deployments to tune requests and limits for resources. We just explained that we were able to use roughly half the memory per sidecar that Istio would request by default. In the most simple flat mesh, every envoy is programmed with load balancing config for every other envoy in the mesh. And when you have a big mesh, that can blow up very quickly. Luckily, there is a solution. Istio provides a Kubernetes custom resource called Sidecar. This resource lets you limit which services are configured as destination endpoints in the client-side load balancing config. So you can use it to segment your mesh by namespace or even with fine-grained workload selectors. Then, the proxies are only programmed with config for the destinations that they need to know about. This greatly reduces config bloat and the memory consumption of proxies, but also the demands on the control plane. It's completely essential to do this at any real scale. bolcom used the Sidecar resource to segment their mesh from the beginning of the rollout, so we don't have a nice graph like the one in this tweet from Carl Stoney at Autotrader UK. It was actually possible to generate all of the Sidecar config because the existing platform automation at Bol had a graph of all the dependencies between the services.
Another fun issue we ran into while enabling sidecars is the fact that currently a sidecar isn't actually a sidecar in Kubernetes. It's just another container running inside the same pod. They're all first-class citizens. While this can be problematic for all types of workloads, the problem with this particularly impacts cron jobs. Since a cron job is supposed to terminate once the work is done, Kubernetes depends on a container exiting with either an error or 0 to determine the successful completion of such a cron job. But since the Envoy proxy is just another container, it'll remain running once the main container is done, effectively keeping the cron job running. The same holds true for starting workloads. Many applications require network connectivity during their initialization. That's a problem if the sidecar isn't ready yet. Native support for sidecars is a feature that the Kubernetes team is currently working on, but due to the many prerequisites, it might take some time for that particular feature to appear in a release. Given our current problems, we weren't able to wait that out, so we needed a temporary solution. Cue Scuttle. Scuttle is a lightweight wrapper for the main container in a pod that blocks until the sidecar proxy is ready to handle traffic, and it will shut down the proxy once the main process terminates. This addressed the problem with cron jobs, as Scuttle is currently recommended for all sidecar-enabled workloads within our setup. Unfortunately, that also meant that most container images had to be updated to include Scuttle, which was a job that needed to be executed by the feature teams, since they were the ones building the containers, in addition to the work they had to perform to make their apps mesh-enabled in the first place.
One of the first benefits of having a majority of the workloads now being equipped with a sidecar was the automatic use of mutual TLS for service-to-service traffic. The sidecars, when they were injected, were configured to use permissive mode with mutual TLS. That meant that service proxies could accept both mutual TLS and plain text connections, allowing both regular and sidecar-enabled services to communicate with them. Initially, we thought that we would need to configure which routes should use mutual TLS, and then a feature called Auto MTLS appeared. Auto MTLS uses the information in the mesh's service registry and will automatically use mutual TLS connections wherever they are supported. And that saved us a lot of extra manual configuration hassle. And while this is a great feature to allow for a seamless migration, at some point the plan is to enable strict mode for most of the applications to ensure security of in-flight data on all of the connections between the services. There are all sorts of applications out there. We've said a bit about needing to customize resource requests for service proxies. We've also found that the reality is that sometimes you'll need to bypass the proxy for certain ports. In particular, bol.com use some technologies like Hazelcast and Zookeeper. These both have some sort of discovery and clustering mechanism. They want to announce their pod IPs directly to each other, and that doesn't work properly with the service proxy in the middle. The solution was to exclude certain ingress ports from being captured by the proxy. And luckily Istio provides annotations to do that. And bol.com teams can use those on their deployments. So if the proxy can be bypassed, what happens to the whole zero trust thing? To fill those gaps, we decided to fall back on network policy-based bulkheads. And of course, that needed to be automated. The bol.com team built a custom Kubernetes controller to watch for deployments with certain annotations and then automatically create the necessary network policies. A network policy was also used to block UDP traffic between namespaces because Istio only intercepts TCP traffic.
And that brings us to the current state of affairs. It's been an epic journey so far, and we're nearing the end of the migration as discussed today. At the time of this recording, we have the Envoy Sidecar enabled for over 91% of all of our workloads across all environments, totaling roughly 3,500 pods. Not all of these workloads have MTLS and authorization enabled yet, but since those migrations are left up to the teams, we're hoping to have the majority taking full advantage of the mesh benefits by the end of August.
Here's a final summary of some things that we think are best practices. Be very incremental. Prepare and educate application teams. They need to be on board. Understand Envoy and its configuration. Use the Istio CNI plugin for injection. Keep a careful eye on data plane resource usage. Avoid config bloat and segment with the Sidecar resource. And allow developers to tune service proxy resource usage for their applications. Test everything carefully and chaotically. Expect to deal with exceptions. We've learned a lot during this implementation and migration, most of which we've already mentioned in detail during this talk. But one last thing to remember is that service meshes are a relatively young technology, and development on most of them is fast-paced as well. So you should be prepared to keep up with those developments in order to make the most out of your implementation, even if that means adjusting your plans a couple of times along the way.
Even though we spent quite some time and preparation to get the service mesh in its current state, we realize we're only at the beginning of the journey, with so many options to explore. But those future adventures will have to wait for another KubeCon presentation at a later date. For now, I'd like to conclude this talk today by thanking James and Google for their continued support, as well as the CNCF, all contributors, and the community for enabling us to build our foundation on awesome products like Kubernetes, Envoy, Istio, Prometheus, and the Open Policy Agent. None of this would be possible without them. Thanks so much for joining us today, and we're happy to answer your questions now.
Thank you.